talk a little bit about hydrology. First of all, what is hydrology? It's basically the study of the water cycle. Everybody remembers the water cycle that you're shown in elementary school. This, goes from rain to evaporation to infiltration and everything. It's just the study of the movement of water. So why do we use hydrology? Well, we have multiple practices that are used to control the flow of water and practices that store water. And in order to design those practices, we need to know the volume and the flow rate of the water that will be affecting the structure. Rainfall events. NOAA has been taking rainfall measurements for a long time, and they've over 8,000 weather stations, and they've used this statistical magic, as I call it, to estimate rainfall volume, duration, and recurrence. And that document's called NOAA 14. Few definitions. Rainfall duration. Well, how long does the rainfall last? It can go from 5 minutes up to 72 hours, or maybe even longer. But we typically focus on a 24-hour rainfall event for designing our practices. Rainfall recurrence interval. I know everybody's heard of the 100-year storm, the 1-year storm, 25-year storm, but the interval, it's basically the probability that the rainfall event will happen in any given year. So if you've got a 2-year storm, that doesn't mean that storm's only going to occur every 2 years. That means that there's a 50% chance of that storm occurring in any given year. In a 100-year storm, you've got a 1% chance of that storm occurring in any year. You can have back-to-back 100-year storms. Rainfall intensity. That's excuse me. That's the amount of rainfall per hour for the rainfall event. That's basically the distribution of the rainfall event. And in Arkansas, we have 3 distribution/intensity curves, and these are the areas. And basically what that rainfall intensity is, when's the downpour going to happen? Is it going to happen in the middle, and how large is that downpour? What percentage of that downpour is part of the rainfall event? This is what the distribution curve looks like. Storm starts out sprinkling, and then it hits the downpour, then it tapers off and starts sprinkling again. Just an example of rainfall and what we use. Let's say we have a pond that we're wanting to build up in Harrison, and there's 25 acres of runoff, and it's got an effective height of 21 feet. What rainfall depth do we use to design the spillway? Well, the first thing we need to do is look at the conservation practice standard for ponds, and that should be the first thing that you do on any structure or any practice, is go and look at the practice standard and read it. But the practice standard for ponds has a table that designates what rainfall events you need to use to design the spillway. And this is the table out of it. And we had our drainage area was greater than 20 acres. So we want to use the 25-year, 24-hour storm to design that. So we'd use a 6-inch rainfall for the design of that. And the good thing, most of our software that we use that's been developed for NRCS that we use for determining the hydrology has these rainfall events built in, or the depths built in. That's the overview of hydrology. Any questions so far?
Hey, Todd, would
Yeah.
you talk about the likelihood? What is the percentage likelihood of a 100-year event occurring in 100 years?
It has a 1% chance of occurring in any given year.
Right.
So you could go 100 years and not have a 100-year storm.
Okay.
And basically how you determine the percentage, if you got a 50-year storm, it's 1 divided by 50 or 1 divided by 100, and that gives you the probability of that storm occurring in any given year. See, we've had, I believe up in Northwest Arkansas, they've had what they determined were 500-year storms in the last 10 years, 2 of them.
Right. So I guess what I was getting at is I think that the percentage of during your 100-year time frame, you have like a 64% chance of that storm actually occurring.
Oh, okay.
And recently read in some of the flood studies that during your life of your mortgage, that 100-year event it has a 25% chance of occurring in a 30-year return period. So that's one of the important things for getting flood insurance. That's free. So sorry to interrupt there, Todd. Go ahead.
That's some more of that statistical magic that
There you go. Yep. Yep.
Okay, let's go to watershed delineation. First of all, what is a watershed? Well, it's all the land that contributes runoff to a specific designated point. And how do we determine a watershed? Basically, we use topographic maps or any type of map that can graphically represent elevations. So what is a topo map? Well, I'm sure everyone's seen topo maps. It's maps that have these lines all over it. Each one of those lines represent a single ground elevation. And this would be a topo map. And to help better visualize a topo map, got this little video. Walt, did that video play? I guess it did.
I was on mute again, Todd. Yes, it did. I'm sorry.
Let me play that again, see. Yeah. But one thing that we'll need to notice on a topo map, these circles are typically going to be the top of a hill, top of a ridge, and if you have the arrows pointing up like that, that's going to be a ditch. If the arrows are pointing uphill, it's going to be a ditch or a stream or a creek. And here's another one that's got a aerial photo behind it to help better visualize what's going on. And if you notice, it's got those, I call them arrows pointing uphill. And if you look right here, you can sort of tell that that's a draw where water's going to collect and run. One thing we need to know about water is water flows downhill, and water will always flow at a 90-degree angle to the contour lines. Here's another little illustration. I'm going to hit points, and it's going to show how the water flows. You notice water's flowing all the way at 90 degrees to those contour lines. And also, if you notice right here, water collects in that draw or that stream. You've got the contour lines with points going upstream. And here, if you've got points that are going downhill, that's going to shed water in all different directions. So some of the important things is to remember that the circles are going to be the top of hill. The points going upstream is going to, or uphill is going to indicate a ditch or a creek or a draw or something like that. So how do we delineate a watershed? Well, the way I do it, and the way I was taught to do it, is first thing I do is I'll put a dot, circle, point, X, whatever it, a point of interest where my pond or grade stabilization or whatever practice we're doing is going to be located. And I determine the general direction of the water flow. After that, I start at the point of interest and go one side, sort of perpendicular to the general flow of water, to the first contour line, cross that contour line at 90 degrees, then go to the next contour line and cross it at 90 degrees. And I keep doing this with each contour. Then I'll go back to the other side and do it on the other side of the point of interest. And you just keep going until your lines meet. So here's say we're wanting to put a pond right here where this red dot is. And by looking, we got a blue line. And the general flow of water is flowing from left to right on the screen. So I'm going to start and go and cross those contours at 90 degrees till I get to the top of the bridge. See, we've got the circle there, so that indicates the top of a ridge. And one thing we always want to do is stop every so often and look and say, well, if a drop of water hits here, where's it going to flow? Well, it's going to flow down here and into the structure. If it hits a little farther up here, it's going to flow completely the opposite direction. So we want to just keep following the top of that ridge. And I got to right there, and a little farther. Right there, and I noticed, I looked and saw, well, we had a drop of water that hits right here, it's going to flow down this other direction. it hits here, it's going to come down and hit and go to our outlet. So we've got to, if you have topo lines with points in opposite direction like this, that's going to indicate saddle. That's what we have here. Continue drawing. We got to peak. And you need to constantly be looking at where water's going to flow. Make sure that you have every bit of water. Start on the other side. And just follow the top of the ridge until your lines meet. One thing, see, we could have moved that point downstream a few hundred yards and we'd have caught a whole lot more water. So sometimes, you know, if you draw one off and the watershed is too large, sometimes you can move it just a little bit and decrease the amount of water that you're getting at the structure a lot. Here's just another illustration of drawing a 90 degrees the contours, the peak. And looking at this, I believe I could have messed up because we've got a draw starting there and it's hard to indicate, well, is that going to come over into this draw or is it going to come back and go here? So probably if you're unsure, this watershed probably should have been drawn. Come up and catch that because it's better to overestimate the watershed than to underestimate the watershed. Here's another example. And when you get to areas that are, the contour lines are sparse, you have to guess, basically, and overestimate if you can. Goes up to the peak. Another peak. Like I said, you always want to be checking as you're going to see where the water's going to fall. See if it fell here, it's going to come down and completely miss. So. One more. Now, one thing about roads, this very possibly could have a ditch right here and all this water could run down and there'd be a culvert down here and completely miss that. But if you don't know, just ignore the road. But if you're going out there and you drive and you can see where the culverts are, it's always best to do that. But in lieu of that, just ignore the road being there. And here's another one that could possibly done the same. Follow the line, contour lines at 90 degrees up until you hit a peak. Follow the ridge. And go until the contours or till your lines cross. Any questions on delineating watershed? It's a lot better to do this in a classroom setting so you can give handouts and have people draw them off and trial and error watershed delineation.
Yeah, I would encourage all of you as you go this summer, as you're in the office, to grab some contour or some USGS quad maps and go ahead and give those a try. Delineate some watersheds, just pick a point and draw some lines and check with your supervisor, see if you're close, if you're yeah, and just practice some of that. It's definitely a skill that is learnable, but it is a little challenging when you first start in on it.
EFH2. What is EFH2? Well, it's a computer program that's based on Chapter 2 of our Engineering Field Handbook. And Chapter 2 of our Engineering Field Handbook is basically determining flow rates and runoff, and it's a method that NRCS or SCS actually developed. And it estimates runoff and peak discharge from small watersheds up to 2,000 acres. If it's over 2,000 acres, you need to use TR55 or a different method. So what information do we need for the input into EFH2? We need the drainage area of the watershed that we just delineated. We need a runoff curve number, need the watershed length, and the watershed slope. Watershed, that's we defined that earlier. It's all the land area that sheds water to the outlet during a rainfall. Runoff curve numbers. They're a number used to help predict direct runoff. In other words, how much of the rainfall will run off instead of soaking into the ground or collecting on plants, etc. You know, after we get a rain, everything out there is wet. You know, you've got droplets of water on your vehicle, on the driveway, collects on the grass and the trees, and that's all water that doesn't run off. And you also have some that soaks into the ground. So to determine the curve runoff, the curve number, you need to know the hydrologic soils group and the land use or land cover. Hydrologic soils groups, they have identified 4 of them. They're A, B, C, and D. A soils have the lowest runoff. They're basically gravels and sands. And then you have D soils, which have the highest runoff and the lowest infiltration rates. They're going to be clays. So you find your hydrologic soils group. It's going to be A, B, C, or D, and you're going to find your cover type. See, we have a 49 for an A, which would be in sandy soil, and an 84 for a D. And come down here to a meadow, and you see that number's lower. Well, why is that number lower? Well, because you're probably going to have more grass if you've got a meadow that you're going to cut for hay instead of pasture that's being grazed. There's more grass and it has more potential to collect more water on that grass. Watershed slope, that's just the average slope of the land in the watershed. And watershed length is the longest flow path that any drop of water in the watershed takes to get to the outlet. Here's an example. This is the watershed, and rainfall hits right here, that water's going to flow down and this way, and that's going to be 10,500 feet. It's up in this corner, it's going to flow this way, and that's going to be 10,800 feet. So this 10,792 would be our longest flow path. So let's say a landowner in Washington County wants to build a pond. That's where he wants his pond to go. So the first thing we want to do is delineate the watershed. So I went into ArcMap and I delineated this watershed. I started on this side and followed contours at 90 degrees, come back to the other side, and I exported that to a shapefile. I created a shapefile, and the reason I did that is I can show you next. But the watershed area is 31 acres. And like I said, I converted that polygon to a shapefile. So our next step is to go into our web soil survey. Went into our web soil survey, and right here, import area of interest. I navigated to my shapefiles, set my area of interest, and there's the watershed. Go up here to soil map, and this tells what type of soils, and this is going to be important later on in determining our slopes. So make sure that you print that out. But we're looking for hydrologic soils groups also. So we'll want to go to Soil Data Explorer, Soil Properties and Quantities, and come down and find hydrologic soils groups and view rating, and it shows us our different hydrologic soils groups. So we've got two different types of soils here, I believe, and they are the same soils group. Okay, watershed slope. You can use the map unit legend to determine the average slope of your watershed. What I typically do is take the average slope of each soil and multiply it by the number of acres of that soil. Add those together and divide by the total acreage in the watershed to get an average. So I've got this Fayetteville fine sandy loam with 3 to 8% slopes, Hector with an average 3 to 40, and so forth. And I took a 5.5 as an average slope for the Fayetteville, 21 average slope of the Hector, and so forth. multiplied it by the acreage of each soil. And then I added up those products and divided by the total number of acres in the watershed to come up with 14.6% average slope. And a watershed length, I tried to find the farthest point, measure that off, tried several different ones to make sure I absolutely get the right one, and we've got 2,006 feet as our watershed length. And then what we want to do is we want to delineate the land use for each individual hydrologic soils group. In this watershed, we had pasture, gravel road, some woods, and some roofs from barns and some houses. And for each hydrologic soils group, I delineated that land use. After we have all that information, we want to open up the EFH2 computer program. Come to your basic data, put your client name. This is really important here. You want to make sure you type in AR for Arkansas, then choose the county. And this was Washington County. And they also indicate next to the county name what rainfall distribution that it's using. This is a distribution 4. After we get that data in, come over here to our runoff curve number. And for each of those land uses that we delineated for the different hydrologic soils groups, you want to put in the acreage, and it'll calculate a weighted curve number for you. Click accept. It's got our drainage area and a runoff curve number that it calculated in the curve number calculator. Next, we want to type in the watershed length, our watershed slope, and it'll calculate the time of concentration. And that time of concentration is basically how long it takes for water from the farthest reach in the watershed to reach the outlet. And after we do that, we want to click on the rainfall discharge data tab. Choose the rainfall type, which was that MWSE4, which came from right here. And it'll populate the rainfall depths for the different frequency storms that we have, 1 through 100. It'll calculate our peak flow and runoff volume. And you'll notice here, for a 1-year storm or 3.6-inch rainfall event, less than half is going to run off. But you get to the higher rainfall events, and more than half will run off. Well, there's only so much water that can collect on leaves and can infiltrate into the soil. Is the reason that the percentage of runoff is greater with the lesser amount of rainfall. Any questions on the EFH2 program? Okay, another way that we can determine flow rate is by using drainage curves. And this is used. You have something, Walt?
I do not. I do not. I was getting ready to chime in if anybody had any questions there. So
Okay.
I do encourage anybody that does go ahead and jump right in.
So what are drainage curves? They're equations for determining runoff for drainage design. And the result of the equation is the flow rate for which the drain is to be designed for. And typically this flow rate is the rate needed to remove runoff from the drainage area within a 24-hour period following a rainfall event. When can we use the drainage curves? Well, basically when the conservation practice standard tells us we can. Basically, it's going to be for structures for water control, drainage ditches, drainage practices. And the practice standard will say if the drainage curve can be used. Here's an example from structure for water control. It comes down here and says the minimum principal spillway capacity for all other structures shall equal the appropriate design drainage curve. And this is the basic drainage curve equation. This top one's at M is for square miles, and this second one here is for acres. We've got C's are drainage coefficient, and A or M is for the area. And this is our drainage curves, and the ones that we use here are for the southeast region. Plus, there's an additional curve called minimum hill. And basically, the only time that will probably be used is around Crowley's Ridge. Other than that, these others will need to be used. So I'm going to show a comparison of why we don't swap the uses between EFH2 and drainage curves. Here's a watershed. It's 169 acres. It's got an average slope of 2%, and this will be our flow length and the watershed length, and that's 7,800 feet. And it's got a curve number of 80. So we put that into EFH2, and for a 1-year storm, 1-year 24-hour storm, we have a peak discharge of 89 CFS. Using a drainage curve, using a 169 acres, we ended up with 13.3 CFS. I'm going to apply a factor safety of 1.25 to come up with 16.6 CFS. And our result from EFH2 was 89. So if we wanted to, if you were doing a practice that called for using EFH2 and you used 16.6 instead, you're probably going to have a failed practice if it's for something other than just drainage. And Walt, I believe that's all I've got for today.
All right, very good, Todd.
Are there?
Definitely want to answer some questions.
Okay.
So if you don't want to speak up here, go ahead and type in any of the questions you might have.
Okay, we've got one here. Is climate change affecting the frequency and the likelihood of the 100-year storms. Yeah, that NOAA 14 that I talked about earlier, that was done in 2014, and the rainfall changed quite a bit from what we were previously using. And if they probably if they'll do another one here in a few years, and it'll probably change again. And you already answered that, didn't you?
Well, that's okay. I was just typing it in. One of the things that I do find interesting is climate models and the prediction on those rainfall amounts. There was a big article in USA Today yesterday on how various agencies don't look at the big picture, and they're dialed into just their little niche, and so it's a big question on prediction on that. Engineering, we're constantly battling what is practical versus what is possible, and trying to always make a good decision on risk. It's all about what can we afford to fail. If it's a high hazard dam, we can't afford to have that fail, so we're going to pick a higher be more conservative, pick a higher rainfall. If it's just a farm pond out in the middle of the country and the dam's embankment's only is less than 10 feet tall, well, we can get by with that 25-year storm through the emergency spillway. So that's what we're constantly looking at on the hydrology. Todd, you want to talk a little bit about our uncertainties in hydrology?
Yeah, there's just I think I remember someone saying if you're within 40% of what actually occurs, they consider you an expert in hydrology. And you just look at all the different inputs and variations. It's just there's just too many variables to get perfect, because you may design it for a 25-year storm with the peak in the middle, and it comes in and that peaks at a different time, and that can throw that, if the storm's actually different than what, that can throw everything off. And just there's just way too many variables. But the method that EFH2 has been proven over 50 or 60 years to be very very close to what happens, and it has I don't know if they've got some overestimation built into it or what, but it's proven to work.
So yeah, the better we are on our inputs, the closer it's going to be, and knowing that the climate itself is, or the storm itself is going to vary from that modeled storm. All right. Well, Todd, thank you very much for that excellent presentation. Oh, here comes another question from Tracy. Have you all checked out the flood factor website? No, I haven't, Tracy. That's a new one on me. I'll go take a look at it though, that's for sure. So, but anyway, if there are further questions, don't hesitate to reach out to Todd, myself, or your area engineer. And we thank you for your attention and for your time this morning. Have a great rest of the day.
I am going to put the presentations in the files part of the chat and Teams, so if anybody needs to download them, they can.
All right, very good. All right, thanks again, Todd. Appreciate you.